Hello and welcome to the first of 3 lessons on the halogens. This is the general introduction lesson and it has specification reference 3.2.3.1 and 3.2.3.2. And our learning objectives for this video lesson are: we want to understand the trends in electronegativity and boiling point of the halogens. We also want to appreciate that the oxidizing ability decreases down the group. That's the ability to take electrons off something else. It decreases as we go down the group. And we want to explain the reaction of chlorine with sodium hydroxide and the uses of the products. Lastly, we'll describe the use of chlorine in water treatment and evaluate the pros and cons. Firstly, let's familiarize ourselves with the halogens. So fluorine I don't have a picture of because it's clear, and in fact fluorine, you can't see it if I had a picture of it. However, chlorine looks like this. We've got a sealed jar of chlorine, so let's put chlorine at the top here. This is chlorine, and it has, depending on its concentration, a slight greeny tint to it. Whereas bromine is a liquid. This is the bromine at the bottom of this jar. The bromine has a sort of deep orange colour. And you see in the top of the jar there, that's bromine vapor that's sealed in the bromine. So the bromine vapor is clearly an orangey colour, and we've got a very deep orangey colour that's almost black as a liquid at room temperature. And the last halogen that we need to consider at A level, because we don't consider astatine, is iodine. And iodine is a solid at room temperature, and we've got these crystals of iodine. And they look rather metallic, they're quite shiny, quite grey. So we've got grey iodine, we've got orange bromine, and we've got green chlorine. So the first thing we're going to do is we're going to familiarise ourselves with the properties of the halogens. And to do that, we'll look at a table. Here's a table that's partially filled, and on the left hand side you see all the halogens in order that they appear in group 7: fluorine, chlorine, bromine and iodine. At least that's most of the halogens. That's still all the ones that you need to be familiar with. And you'll notice from the formulas that they're all diatomic molecules. They all share 1 electron each to give themselves the full outer shell. So that's the formulas that you're familiar with, and the colours we saw in the previous slide. Fluorine is actually a very pale yellow. You saw perhaps a pale green colour for chlorine, and more green is more concentrated it gets. A reddy brown, I called it orange, for bromine, and a grey colour, dark grey colour for the iodine. Let's look at the physical state. So, as far as physical state is concerned, our first two, fluorine and chlorine, are gases, and we have liquid bromine and solid iodine. And then we're going to move on to the electron configuration of the atom. Now, of course, they all have 7 electrons in the outer shell, but in each case, because they're in one extra period as you go down the group, they're going to have an extra shell of electrons. So here it is. So with fluorine, we've just got our second shell, 1 short of an electron. And in chlorine, we've got 1s2, 2s2, 2p6. And then in the third shell, we've got 2s2, which is full, but 3p5, which is 1 short, because there's 3p orbitals, each have 2 electrons, you remember. So the p orbitals want 6, and so the p orbitals are 1 short there, which makes the whole third shell one short. As far as bromine is concerned, not only have we filled in our p orbital, but we've also gone back to our 3d orbitals, the 5 3d orbitals, and we filled those in. That was done after we filled in the 2 electrons to go into the 4s. And you'll notice that there's 5 electrons in the 4p shell, and all the p's want 6, and so it's one short there. So bromine is there, one short of the 4p orbitals. And as far as iodine is concerned, same sort of thing. Our 4p electron's been filled in, but so has the next 2 electrons that get filled in, be the 5s2, and then you go back and complete the 4d shells. So there's the 10 electrons that go into the 5 4d orbitals, and then only 5 out of 6 of the p orbitals are filled. So it's one. So iodine is one short in its 5p orbitals. So what that illustrates is that the atoms start off very small with fluorine and get very large with iodine. So these these electrons that are in the 5p orbitals are a long way away from the nucleus, whereas fluorine's electrons in the 2p orbitals are pretty close to the nucleus, and that's going to affect all sorts of properties, particularly its electronegativity. Okay, what we're going to do now is we're going to have a look at 2 properties of the halogens. We're going to have a look at boiling point and electronegativity. So in terms of boiling points, let's do that on the left-hand side of this representation of the group 7. So boiling points of the halogens increase as we go down the group. So boiling points increase as we go down the group, illustrated with this scrappy little arrow. Let's explain why. So let's draw fluorine first. I'll draw it in a pale colour. So fluorine is a small atom. Let's represent it like that. Whereas iodine, I'm going to draw that in grey because that's grey. Right, iodine is a big atom. That doesn't look very grey, does it? Let's do it in black. Okay, so iodine is a large atom, and the difference in size would be much bigger than is represented here. But I don't have that much space. So boiling points of simple molecules like these are all simple molecules, little diatomic molecules, and when you're dealing with diatomic molecules, the boiling points always depend on the van der Waals forces. So I think you'll have come across that in another topic. But with a small molecule, the van der Waals forces are weak. So it's weak and strong with a larger atom. Why are they weak and why are they strong? That's the question. So van der Waals force happens because electrons don't hang around in the same place at all. In fact, it's impossible to determine both the location and the momentum of an electron that you might come across in physics. Okay, but because of that, at a particular instant in time, electrons might be, let's draw my electrons in red. Electrons might be slightly more on one side of the electron, one side of the atom than the other, in which case there would be a very temporary small negative charge there, which would leave a very small positive charge on the other side, because that's just got a dearth of electrons if they happened by chance to be instantaneously on the other side of the atom. But because the distance is small in a small atom, the distance is small just from there to there across the diameter of the molecule in this case, then the van der Waals forces are weak. So they have a small attraction. So if we had another fluorine molecule here, then that negative cloud that's drawn in red there would repel the electrons in this other molecule to the other side, and it would leave a small positive charge behind it. So you can see a slight attraction. Let's draw an attraction in black. You can see a slight attraction there between the very temporary negative charge on the first fluorine molecule that I drew, and a temporary positive charge on the second fluorine molecule that I drew. So those forces are weak because the atoms are small. Now we've gone down through the periods, and an extra whole period in chlorine, another further one in bromine, and a further one in iodine. So iodine's much bigger. So exactly the same thing is happening here with iodine, except the distances are large. So that means that at any particular instant in time, you can have by chance a larger negative charge on one side of the atom than on the other side. So that leaves, if the electrons just happen by chance to be on one side, that leaves a positive charge on the other side, and because the distance is greater, the separation can be greater, and therefore the charge, this tried to draw the delta minus there slightly larger than with fluorine, to illustrate the fact that because of the distance, the charge can be slightly larger. And then what that's going to do to an adjacent iodine molecule is it's going to force these electrons by repulsion over to the other side of the second iodine molecule, leaving behind it a positive charge. And that attraction there, in the case of iodine, is much stronger. I tried to draw more closely adjacent black dashes in the case of iodine than I did with fluorine. So there we have it. Summary is that the boiling points increase as you go down the group because the atoms get bigger, and because the atoms get bigger, the van der Waals forces are stronger, and that explains the increase in boiling points. So there we have the first explanation, the first property rather. Let's now think about electronegativity. Yeah, so electronegativity, you remember, is the tendency of an atom or an ion or a molecule to attract electrons, particularly a bonding pair of electrons. Okay, and electronegativity depends on three factors. The first is nuclear charge. So if everything else was equal, a high nuclear charge, so let's say there were 10 protons in a nucleus, everything else being equal, that would attract electrons more strongly than would a nucleus that had only 2 protons in it. Okay, so nuclear charge, the first one, and the second one, in no order, is shielding. Shielding is the word used to summarize the concept by which complete shells of electrons shield electrons that are further away from the nucleus from the nucleus. Right, so if you've got an outer electron that is in between it and its nucleus is 2 complete shells of electrons, then that outer electron is going to be attracted less to the nucleus than it would be if those 2 complete shells weren't there. So those 2 complete shells are shielding that outer electron from the nuclear charge. the positive nuclear charge. So that's shielding, you remember, and the third one is distance from the nucleus. So therefore, let's consider two cases again. One electron is a long way away from a 10 proton nucleus, and the other electron is close to a 10 proton nucleus. Clearly the one that is closer is going to be attracted more strongly than the one that is further, everything else being equal. Okay, so your electronegativity depends upon those three factors and how they combine. Okay, so let's think with fluorine. Let's switch back to blue, and electronegativity increases as you go up the group this time. Increases, up the group. So fluorine is more electronegative than iodine. Okay, that's a statement of fact. Let's explain it. So why is fluorine more electronegative than iodine? Well, let's think about its nuclear charge. So the nuclear charge for fluorine is less than for iodine. Iodine's got a much bigger nucleus than fluorine. So that would have an adverse, that would not increase its electronegativity. So why don't we do it like this? So nuclear charge, I'll do a column here. So we do fluorine versus iodine. So nuclear charge is going to be less. Now, what about shielding? So shielding. So you remember with iodine, iodine's got is way down in the group, so it's got lots of complete shells of electrons. So the shielding of iodine, so shielding is going to be less for fluorine. So we'll do fluorine versus iodine. So the shielding is less in a big way, and distance from the nucleus. Distance from the nucleus is also going to be less. So the fact that nuclear charge for fluorine is less than iodine is going to make the electronegativity smaller, but the shielding is going to make the shielding being less is going to make the electronegativity be higher, and the distance from the nucleus being less means the electronegativity is going to be higher also for fluorine. So the net effect of all those green arrows is that fluorine is a lot more electronegative than iodine. It wants electrons much more than iodine, and in fact much more than any other element in the periodic table. Okay, we're going to illustrate that trend in electronegativity using displacement reactions. First of all, let's remind ourselves what a displacement reaction is. So you might remember when we did the reactivity series of metals, you would put one metal into a compound and to see if the metal would displace the other metal that's in the compound. And for example, let's say we put some potassium into some sodium chloride. Potassium is more reactive than sodium, so you would get so the potassium would displace the chloride, and you would get potassium chloride and sodium left. So you remember those reactions, they're displacement reactions that gave us at GCSE the reactivity series of metals. We're going to use those with the halogens and halides now to explain the oxidizing power So the oxidizing power comes from the electronegativity. So if something is very electronegative, it's going to have a high oxidizing power, and vice versa. So what we can do is we can look at a table here, and let's explain the table. Looking at the columns, for example, we've got some potassium chloride in the first data column, and we've got some potassium bromide in the middle, and we've got some potassium iodide. So potassium is the same in each case, but we've got a halide. So let's just illustrate what's important about the columns. The important thing about the columns are the halides. So we've got chloride, bromide, and iodide. And what we're going to do is we're going to react to them with halogens. Okay, so we've got halogens here. We have chlorine, we have bromine, and we have iodine halogens, or halides. So we're going to put the halogen into a halide and see if it displaces. So let's start with the first box here, this box that I've just annotated there. So we're going to add chlorine to potassium chloride. Okay, so chlorine and chlorides, halogen and halide, same thing, so we're going to have no reaction there. And while we're at it, let's fill these boxes in as well. So we're not going to get a reaction when we put the halogen into a solution of the halide, same halide. So let's also notice in the second one that the three halides are all colorless. Okay, so halides are colorless, whatever they are, but the halogens are either colorless in the case of chlorine, or orange or brown in the case of bromine and iodine. So we're going to notice changes if we see a displacement reaction. We're going to notice changes in colors. So let's say we have a solution of potassium bromide. So we're dealing with this box here that I've just put a little mark in, and we're going to add chlorine to it. So it's just chlorine gas dissolved in water. We're going to add that to a solution of potassium bromide, and because chlorine has a stronger oxidizing power than bromine, it is going to displace the bromide from the potassium bromide, and that means that you will see the bromine, the halogen bromine, you will see that created. So the chlorine will disappear. All right, it's already colorless, but it stays colorless as a chloride, and what you will see is the colorless potassium bromide. You will see that turn orange. So the orange solution, because what you've done is you've turned your bromide, two of them, into bromine with a displacement reaction, like that. And let's say so we're going to move on to this box here that I've just put a mark in the corner of. So let's say we do the same with chlorine. So we've got some chlorine water, and we're going to add that to iodine. So which is the most powerful oxidizing agent? Well, of course, chlorine is. Versus iodine. So the chlorine is going to displace the iodide from potassium iodide and form potassium chloride, and the iodide is going to be chucked out of the compound and will have to form the element iodine instead, so I2 instead, which is brown when it's in solution. Okay, so we're going to see two iodide ions, making an iodine molecule in solution, and that's going to mean there's a brown solution formed. Okay, so that's the row that is chlorine. Let's do the same with bromine. So how strong an oxidizing agent do you think bromine is? Well, the electronegativity would suggest, the trend in electronegativity that we did on the previous slide would suggest that it is stronger than iodine but weaker than chlorine. So let's see what would happen here. So if that is true, what would happen is that the bromine would not be able to displace the chloride from potassium chloride. All right, so the chloride would stay as chloride and wouldn't come out, and so you would see no reaction here. So you'd see no reaction. Bromine wouldn't be able to displace the chloride and make it into chlorine. Chlorine would keep its extra electrons that it's got from the potassium. It wouldn't give them up to the bromine because it is more electronegative than bromine, and consequently it is a stronger oxidizing agent than bromine. Okay, so now let's go along to the end column for bromine and fill in this box here. So we're adding bromine water to potassium iodide solution. So is bromine a stronger oxidizing agent than iodine? Well, it is. And so what you're going to get is the bromine is going to come along and it's going to see an iodide ion with an extra electron, right? And it is the more powerful oxidizing agent, so it's going to say to the iodide ion, I'm having that extra electron, and it takes that extra electron from the iodide that used to be with the potassium. So the bromine turns from a bromine element into a bromine ion. So we've got, and the opposite happens with the iodide. So the iodide had that extra electron to make it an ion that it had got from the potassium, and it gives it up to the bromine. So the same reaction happens. You've got two iodide ions, and they're going to form an iodine molecule. So instead of having its own extra electrons, it's going to have to share electrons with another iodine atom to make an iodine molecule. Right, so we're going to get a brown solution formed. So just don't get confused with the colours, because brown's quite similar to although iodine as a solid is grey, as in solution it's brown. So that's why we've got brown solutions here. Okay, so that's that. Now let's move on to the last row, the iodine solution row. And is iodine a stronger oxidizing agent than chlorine? Well, no, it's not, because it's at the bottom of the group. Right, so iodine can come along and it can quite fancy the electron that the chloride has got, but the chloride is going to have nothing of it, and it's going to keep its extra electron, and so the iodine is going to have to stay as iodine. All right, so you're going to get no reaction. And that's going to be the same with bromine, isn't it? So the iodine can come along and it can look with envy at bromide's extra electron that the bromide got from the potassium, and it can have a go at getting it from the bromide, but the bromide is the more powerful oxidizing agent. It's the more electronegative, so it's going to keep its electron, and iodine is going to have to stay as iodine, so you're going to get no reaction there either. Okay, so they are our, just to summarize that last slide, they are our displacement reactions, which illustrate experimentally the trend in electronegativity and as you go down the group. Now we're not using fluorine because fluorine is very dangerous, but I think you could quite easily imagine what would happen with fluorine. In fact, fluorine, you couldn't do this experiment because fluorine would oxidize the water that you tried to dissolve it in. Right? So you couldn't get F2 dissolved in water because it would react with the water. It would actually displace the oxygen from the water molecule. So that's why we don't do fluorine with this practical. Okay, so if we look back at our table that we started with, what we can do now is we can just illustrate experimentally what you might do in the lab, and we might well do this in the lab. So what we're going to do is we're going to do 2 of these actual experiments. What we'll do is we'll add some chlorine water to some potassium bromide. So we are going to do experimentally, we're going to do this reaction here, and we'll also do this reaction here. Alright, so that's what I'm going to do on the slides, and in the lab we might do the others in reality as well. So here we have some test tubes and some droppers and things, and let's write down what we're doing first. And with this one, we're going to add some chlorine water. So the important part of that is the chlorine, and it's aqueous, so it's chlorine water, and we're adding that to some potassium bromide. And we're going to need 2 of those because we've got a chlorine molecule that we're starting with. That's also a solution, and there's going to be a displacement reaction there. So you're going to have 2 potassium chloride ions. So yes, you're going to have 2 potassium chloride ions, and you're going to have bromine having to share electrons in a molecule instead of having its own electrons, and that's going to stay dissolved in the water. So that's the reaction we're doing in the left-hand setup. I'll just change colour so we don't confuse it with the right-hand column. So in the right-hand column we'll do the other reaction. So we're going to add some bromine water. So it's bromine dissolved in water, and we're going to add that to iodide, potassium iodide, if you remember. So again, we're going to need 2 moles of potassium iodide in solution, and again there's going to be a displacement reaction happening, and it's going to give us 2 moles of potassium bromide. And the iodine is going to be kicked out and has to make do with sharing electrons between 2 of its own kin. Okay, so let's just explain what we're doing in the first. So we're moving back over to the chlorine reaction on the left-hand side, and in the dropper we've got some, let's do that in black, in the dropper we've got some chlorine water. So this is our Cl2 aqueous, and that's colourless, pretty colourless, yeah. So although it's green as a gas, it's colourless when dissolved in water. And this solution here in the test tube, this colourless solution in the test tube, is a solution of halide ions. So halide ions. Now let's say, for example, we didn't know which halide it was, and we wanted to know. That's the experiment. So we're dropping chlorine into the halide ions, and it could either, if it was chloride ions, nothing would happen. If it was bromine ions, we'd see some bromine being created, so we'd know it was bromide ions there. And if it was iodide, it would go brown, and so we would see, we would know that it was iodide in the left-hand test tube there. So when in this experiment we're adding it to potassium bromide, so we're going to have bromine dissolved displaced out of its compound with potassium, and that's orange. Although it might not look orange on the slide, that's probably what you would see. That's orange. So we could write that as a reaction, shall we? Okay, so we've got as an ionic reaction, that is. So in an ionic reaction, we just include the things that have changed. So potassium's not changed; it stayed as a cation, as a reactant, and as a product, it was still a cation. So the things that changed were chlorine, aqueous, and that reacted with two bromine ions that were also aqueous, and they formed two chloride ions and one bromine molecule dissolved in water. Okay, so that's the ionic equation for the balanced equation that we have on top. Okay, so good. So if we didn't know what halide ions were in the left-hand test tube, we would have found out because we saw that it went orange when we added chlorine to it. Okay, so let's do a very similar experiment. Let's say we didn't know what these halide ions were. All right, it's a solution, and all halide solutions are colourless. So even though, you know, I've already told you that it's potassium iodide, if I hadn't told you that, you wouldn't know, because it's the same colour as the potassium bromide was in the first place. So in this case, we're going to add bromine to it. So we've got some bromine water, just the bromine molecules dissolved in water. And just like this was orange, this is going to be orange as well. So we drop those into the unknown halide, and hey presto, what we get out of the after the displacement reaction is we get a brown solution. We get a brown solution because it's brown and not still colourless and not orange, because it's not the other two possibilities. We know that what we've got is iodine water, just iodine molecules dissolved in water. Okay, so we've already got the main equation. Let's draw the ionic equation. In the dropper, we started off with bromine, and we added that to iodide ions, and we had two of them. Well, we need two of them rather. So two iodide ions that were happy with the potassium, and they went through a displacement reaction because bromine is more electronegative than iodine, and so the bromine atoms stole the iodine's electron and became bromide ions, and there'd be two of them, and the poor old iodine lost its electrons and had to go back to being a molecule because it was bullied by the bromine. Okay, so that's our ionic equation to go with our full equation, and hopefully that's illustrated a bit more practically what we did on the previous slide theoretically. Okay, so how do we make it? How do we make it? Well, we make it starting off with chlorine gas. So we're going to have some chlorine gas, and we're going to react that with some sodium hydroxide. We react that with sodium hydroxide, and we use cold, actually room temperature, which is cold compared to most chemical reactions in industry. So cold and dilute. Cold and dilute sodium hydroxide reacted with chlorine gas, and they react. It's a disproportionation reaction, which I will explain in a second. So then we get our bleach, sodium chlorate, which looks like that, and that's also in solution. And we get some sodium chloride and some water. So sodium chloride is in solution and water is obviously liquid. Okay, so I mentioned that this was a disproportionation reaction, which is a word that you, if you're not familiar with, make yourselves familiar with it. So it's a disproportionation reaction, and what that means is, I'll draw the meaning up here, what that means is that something is both oxidized and reduced. Something is both oxidized and reduced in the one reaction. Right, so let's see what it is. So if we're talking about what's being oxidized and what's being reduced, what we'll have to do is we'll have to work out what the oxidation states of the chlorine is in each of the compounds here. So let's start off with this one here. So you'll remember from oxidation numbers that elements have an oxidation number of 0, even when they're in diatomic molecules like this, because they're bonded to an identical atom. So the oxidation of chlorine here is 0. Now this is moving on to the products here. What we have is we have a sodium ion and a chlorate ion. The sodium is 1+ and the chlorate is 1-. And so the chlorine here, let's work out the oxidation number of that. So the oxygen, we know that apart from in hydrogen peroxide and any compounds with fluorine, oxygen is going to be 2-, because oxygen is more electronegative than chlorine. So if oxygen is 2- and the ion itself is 1-, then the chlorine in that chlorate ion must be 1+, +1. Okay, so go through that, rewind and go through that again if you didn't quite get it first time. And we've got another chlorine over here, okay, in the sodium chloride, and sodium is a 1+ cation, and the chloride is a 1- anion, and so it's clear that our oxidation number of the chloride is -1. So as you can see, going back to the word disproportionation, as you can see, you had 2 chlorine atoms in our chlorine molecule to start off with as our reactant, and one of those chlorine atoms has been oxidized, the one in the sodium chlorate, with an oxidation number of +1, and one of them has got itself an oxidation number of -1, and that's been reduced. It's gained an electron. Okay, so that is the reaction that creates bleach, and on the previous at the start we talked about the uses of bleach, and that's what you need to know about bleach. So as you know, when you've been swimming, the distinctive smell is due to the chlorine in the water. So we're going to study that reaction between chlorine and water, and it is in fact also a disproportionation reaction. And here it is. We start off with some chlorine. Gas. We're going to bubble chlorine gas through some water. And you get some chloride ions. So that's the chlorine atom that has been reduced. And you get some chlorate ions. And that's the chlorine atom that has been oxidized. Its oxidation number is going to be +1 in there. And of course you've got 2 hydrogen ions being left over from the water. And each of these is aqueous. We'll just review the oxidation states of chlorine. We've got 0 here as the element. We've got -1 as the chloride ion, and we've got +1. So that's the disproportionation reaction again. Disproportionation reaction again. And so that's what you swim around in when you go to the swimming pool. And in fact, if there was a lot of sunlight involved, chlorine can oxidize water, which is quite interesting. And if it were to do so, it would look like this. Again, we've got some chlorine gas plus some water, and this is an equilibrium reaction because the equilibrium is way over to the left. So it's not by any means a complete reaction. So you got your hydrogen ions and you've got your chloride ions this time, and because the chlorine is oxidizing the water, the oxygen is left as an element. It's being displaced from water by chlorine. Put half in there just to make sure it balances, and that will escape as a gas. You get oxygen gas coming off that in sunlight. So let's just write our sunlight in here. And it's a good idea to be familiar with that reaction. What you don't have to be familiar with, but what you might be interested in is why. Why do we get this? Why is chlorine able to oxidize water to take the electrons that came from hydrogen, take them off the water, off the oxygen atom, and leave the oxygen as an element to escape as a gas? Well, how can that happen if chlorine is less electronegative than oxygen? That's not going to be in your AS level or your A level, but if you were thinking of doing Oxbridge, then that's the sort of question you should ask yourself and have a go at answering. And if you're interested in the answer, come and see me. Okay, the last little topic in this video lesson is about water treatment, i.e. the addition of chlorine to our water before we drink it. And there are pros and cons. Some people think we shouldn't have chlorinated water because it's not an absolutely clear-cut case that we should, even though pretty much every country in the Western world does add chlorine to their water. So anyway, let's go through the pros and cons by means of a table. Pros, cons. Okay, so the first thing is to realise that the chlorine or chlorate ions, they kill bacteria and microorganisms. That might otherwise cause disease. And that's the main reason why chlorine is added to water. But also, chlorine also prevents growth of algae, which would otherwise smell and look ugly around any sort of settled water, like pipes and plants. So it prevents the growth of algae as well, and also removes discoloration. So some of the organic compounds that might be in water from plant decomposition, for example, would be coloured, and people don't like those colours. They don't think they're clean, and basically the chlorate will bleach it and make it look cleaner. So we'll summarise that by saying removes discoloration. Okay, so the three main pros are listed out there, with the first one being the most important, in my view anyway. You have your own views. So moving on to the cons then. Let's do the cons in red, shall we? So the cons, primary one is that chlorine is toxic. Especially if it's breathed in as a gas, it's very harmful to the respiratory system. And so although, you know, the water that comes out of our taps is not putting us at risk of breathing in gaseous chlorine because it's been added to the water, you could possibly have accidents at water treatment plants that could be serious, even fatal. So let's just annotate that by accidents at water treatment plants could be serious. So that's one, and the second one is that that chlorine reacts with organic compounds, those same organic compounds that we want to remove the discoloration of. So the organic compounds that might come from plant decomposition that find their way into the water system, chlorine can react with those organic compounds, and the products of that reaction are sometimes carcinogenic. So you get chlorinated hydrocarbons, some of which are carcinogenic. So let's make a note of that. So chlorine reacts with organic compounds from plant material that find their way into the water system and would carcinogenic. So some of those products of some of those chlorinated hydrocarbons are carcinogenic, which is obviously a risk, but it is generally accepted that it is a much smaller risk than the untreated water. But nevertheless, it requires us to assess pros and cons before we make a decision. So the big risk with untreated water is, of course, cholera. And a cholera outbreak would kill thousands of people, and has done many times over history before we treated water. And we don't get cholera anymore because we treat our water with chlorine. And that's the big risk. And the smaller risk is that the chlorine reacts with the organic compounds, making chlorinated hydrocarbons. Okay, so there's the pros and cons of water treatment. Be familiar with them. You've basically got 3 pros and 2 cons to remember. And that should do you for that. And that completes our video lesson, apart from just making sure we've done our learning objectives. The first of which was we wanted to understand the trends in electronegativity and boiling point of the halogens, and we certainly did that. And we wanted to know that the oxidizing ability decreases down the group. Oxidizing ability is the same trend as electronegativity. And we want to explain the reactions of chlorine with sodium hydroxide to make bleach, and also with water to, that's in the next learning objective. And we wanted to list out the uses of bleach. So we did those 2, and the last one was describe the use of chlorine in water treatment and evaluate the pros and cons. So we had 3 pros and 2 cons, and if you remember those, you can get yourself your A star. Thank you very much. I'll see you in the next video lesson.